Hi, I'm Eric Reese, Senior Vice President of Memory and Storage Strategy with KIOXIA. Here together with
Rory Bolt, a Senior Fellow at KIOXIA and a Principal Architect on the CEPH Technology Project.
We're here to talk about why are you still using flash like a drive. This is an introduction to a new technology that we're going to announce called software-enabled flash. As we look around in our hyperscale software-defined world, we're noticing that the hyperscale data centers have been redefining the use of flash storage within their environments. We think that this is because all of the current existing solutions that attempt to address storage at the massive scale are extensions of the hard drive paradigm, when what is really needed is the ability to combine the speed of flash with the ease of software definability. And I'd like to discuss a little bit about the motivations behind this redefinition. And I think it's quite simple. So we want the benefits of flash without the traditional overhead that comes with the hard drive paradigm. And in the upper left, we see listed some of that overhead. In reality, we want the speed, the media density, the non-volatility of flash without having to worry about this overhead, which is in reality a tax on the flash storage at the hyperscale. Well, with software-enabled flash that we're introducing today, developed by KIOXIA, we think that you can have your cake and eat it too, because this technology provides the hyperscale developers with enhanced control over the behavior of their storage while reducing the burden of media management. Let's talk a little bit about how that's done, a little more about what software-enabled flash is. It's a media-based, system-centered approach that we believe fundamentally redefines the relationship between the host and the software and the solid-state storage. It does that by bringing control of the media to the host. I'm going to skip a bullet here, and it does that because it's coupled with purpose-built hardware and the flash-native API. Together, these resolve the traditional overhead problems listed on the right here that I talked about on the previous slide. This open source API leverages industry standards and protocols. The standards of PCIe and toggle together with NVMe commands. Host applications have complete or partial control over the storage functionality as defined by the needs of the data center. Finally, we believe it maximizes the flexibility, performance, and speed of the flash. In other words, its value. Now, CEPH is not software, it is software enabled. I'm going to talk a little bit about the API and some of the things related to that. So as I said, it's a software enabling technology built around an API that is flash native. This API will be open sourced, and KIOXIA will be providing sample code and libraries to enable those who want to adopt it or to investigate this technology. This API is designed so that any flash supplier can engineer their device to execute this API, hopefully enabling multiple sources of this technology in the marketplace. Finally, as a platform, together the API, the SDK, the purpose-built hardware as a platform, it can implement multiple technologies such as block, flash native, or ZNS. Now, to wrap up this introductory portion here, I just want to recap that SEF, we believe, and I'm very confident, is a powerful way forward for flash in the hyperscale environment, a way for it to shed the legacy hard drive paradigm and open up the greater flexibility, density, and other benefits of flash, in fact, even its digital nature. Because of this, and with this technology, flash can behave in a much more predictable and uniform manner, which will also lead to better latency outcomes. It can be used at its native speed, and also delivers tools that you'll need for your developers to be able to continue to move forward without having to worry about a lot of the other problems that generally come, such as generational differences. Finally, SEF technology brings software flexibility and scalability to flash. Now that I've talked a little bit about what it is, I would like to turn the time over to Rory, who, in developing this technology, can tell you how it works.
Thank you, Eric. Well, welcome to my home office. I hope everyone's enjoying this virtual conference. I'm going to be talking a little bit more about the technology behind CEPH. CEPH consists of two major components, a hardware component and a software component. The hardware component is focused on the management of the flash media itself and trying to address the requirements of the hyperscale customer. So each flash vendor has subtly different flash products, and each generation of flash from each vendor is subtly different from each other. We want to hide that. We want to abstract this out so that end user host code isn't affected by these differences from generation to generation and from flash vendor to flash vendor. Next, the hyperscalers demand tight control over die time scheduling. So we want advanced features to support that requirement. We're going to give access to the entire flash media with no over provisioning built into the product itself. We're going to accelerate functions related to flash media management and offload the host for maintenance tasks within the flash itself. And finally, we're going to allow for very flexible DRAM configurations of the hardware, and we'll be talking more about why that is important to the hyperscale customer. On the software side, we're going to provide an API and libraries that support this functionality. The hyperscalers demand control over data placement, isolation of workloads in tenants and multi-tenancy environments, control over latency, help with buffer management, and adaptability to new workloads. The hyperscale environment is a very, very dynamic environment with change happening at a daily rate. So, how are we going to do that? Well, let's take a look at the hardware first. This is a high-level block diagram of an SEF unit controller. You'll notice that at the top of the diagram, it is a PCI interface to the system. At the bottom of the diagram, this particular controller is implementing the industry standard toggle interface to talk to flash. Other controllers could use other flash interfaces such as ONFI. The important thing to note is that industry standards are used wherever possible, and that the actual logic of the controller itself is focused on media management. So the controller is going to handle all the low-level programming algorithms necessary to support the flash associated with it and abstract out the differences from this flash versus other flash. Likewise, the controller is going to implement all the lifetime extension techniques and defect management techniques particular to this flash. Once again, abstracting those details out from the higher level software. In addition to this media management, the controller implements prioritized and weighted queues at a per die level to give control over latency in the system. It implements copy offload functionality to accelerate both garbage collection as well as wear leveling, and it handles the low-level ECC generation and checks for the flash media itself. Finally, there is a DRAM controller, although DRAM is optional. There are deployments of SEF possible that use SRAM only. Now a high-level look at the software associated with CEPH. We're going to be supplying a software development kit, and in that kit, you'll get four main things. There will be an open source Linux reference block device driver. There'll be an open source Linux reference flash translation layer. There'll be an API library that provides C and C++ language bindings to all the functions within CEPH, definitions for all the data structures, enumerated types, as well as utility functions that make interfacing and adapting to CEPH easier for programmers. The combination of the hardware and the library will abstract out all the details of generational differences and vendor differences for the supported flash, and the API library also allows you to define the scheduling policies and control the latencies within the device. At the bottom layer of the stack is the CEPH device driver. This is a lightly modified NVMe device driver that's been extended to support the SEF command set. One final note on the software block diagram, you'll notice that the SEF API library is depicted as an L shape that reaches all the way up to user applications. In fact, we are working on reference implementations of the ROCS database program that are Ceph native, allowing bypass of the operating system and direct control over the flash to minimize write amplification, as well as to maximize the performance of the ROCS DB application itself. Now I'd like to introduce 3 concepts that will be useful in understanding the Ceph technologies. The first concept is that of a virtual device. So a SEF controller can control many channels of die and many banks per channel. In this particular instance, we've divided a single SEF unit up into 4 virtual devices. We've assigned individual die to virtual devices, and this provides a hardware level isolation of the virtual devices. An individual die is never shared between virtual devices. It's a one-to-one mapping. Finally, when you're specifying a virtual device, you have control over how many channels the virtual device spans, as well as how many banks it spans. This gives you control over the capacity of the virtual device, as well as over the bandwidth available to that virtual device. The next concept we're going to introduce is that of a QoS domain, or quality of service domain. And this is a mechanism that allows us to impose capacity quotas, as well as scheduling and policy to provide software level isolation within a virtual device. So a typical SEF unit may have 64 or 128 die, but in the hyperscale environment, you may need to partition that to support hundreds, if not thousands, of users. The QoS domain allows a software level of isolation within these shared devices and allows you to support very, very fine-grained allocations within a Ceph unit. The final concept is that of a placement ID. When you define a QoS domain, you get to specify how many placement IDs will be supported by that QoS domain. And the SEF controller guarantees that data written to different placement IDs will never end up in the same superblock within a QoS domain. And so this concept allows us to provide placement control down to the superblock within QoS domains that are shared within virtual devices. The next topic is that of die scheduling and queuing. This is a very advanced feature set within the SEF controller. We define 8 command queues per die within the Ceph unit itself. These queues, labeled Q0 through 7, are prioritized, with Q0 being the highest priority and Q7 being the lowest priority. In addition to having priorities, each individual queue can supply die time weights for each type of flash access command, erase, program, or read commands. And through the combination of these, we can implement various different scheduling functionalities. If you set all the weights to 0 across all the queues, then it works as an 8-way prioritized scheduler. If you set all the weights to the same value, it has to be a non-zero value, it'll work as a round-robin scheduler across the 8 queues. And if you specify unique weights for the read, program, and erase functions, it will work as a die time weighted fair queuing scheduler. So once again, there are 8 command queues per die on the Ceph unit. The device scheduler handles all suspend resume logic for program and erase commands to allow read commands to interrupt them to honor priorities of the queues. You can specify the individual die time weighting separately for read, program, and erase commands. You can specify the queue assignment for each flash access command per QoS domain. So you could have one QoS domain submit its reads to Q0 and a different QoS domain submit its reads to Q1. Both QoS domains could submit their writes to Q2, very flexible system. And finally, we allow individual commands to override the policy that's defined for the QoS domain. And we'll see how that can be used in a couple of slides. So this slide is going to introduce the notion of latency control in a CEPH unit. The first graph depicts a typical latency profile for a standard SSD. The majority of commands have very low latency, but you see a long tail with a few commands having very, very high latency. This is typically caused by a garbage collect or some other internal housekeeping command within the device. This second latency profile has a much tighter distribution. In fact, the absolute shortest latency is longer than the first graph, but the longest latency is shorter than the first graph. The average of the two graphs is the same. Which latency profile is better? Well, it's actually a trick question. It depends on what you're trying to accomplish. What SEF does for the first time is give the host total control over the latency profile of the device and the ability to change it in real time. So what are the mechanisms that allow this? Several of the ones we've already introduced. The isolation of workloads by virtual devices and the policies associated with QoS domain scheduling, the mapping of commands to prioritize queues per die within the domain, the weighting of the commands, the automatic handling of program erase, suspension, and resumption. And as I noted on the previous slide, the ability to override these defaults. In particular, for a garbage collect operation, you can actually adjust the die time weighting to account for the instantaneous write amplification that's being observed in the system. And this is an unprecedented level of control and a really neat feature of the SEF controller. In addition to this, all of the host maintenance, all of the drive maintenance commands are controlled by the host. Total control over when garbage collection occurs, as total control over when wear leveling occurs, and total control of the host by the host of the patrol operations within the device. The final technical topic I'm going to introduce with SEF is that of unified write buffers. In a traditional SSD architecture, the write buffers are held within the drive itself. In the hyperscale environment, it is not uncommon to have hundreds, if not thousands, of simultaneous write streams destined for the same device. Each individual write stream needs an independent write buffer to order its data. With a conventional architecture, you have to size the write buffers in the drive to handle the worst case load that you ever anticipate the drive will encounter. If you don't actually encounter that worst case drive load, that RAM in the drive, that DRAM reserved for the write buffers, is essentially a captive resource that you've paid for that you can't take advantage of. With unified write buffer architecture, you can use write buffer memory in the host. And it's not unusual for the hyperscale environment to have non-volatile, high-speed random access memory available for these purposes. And so by leveraging that write buffer capability in the host, you can adapt dynamically to surges in demand and not have to pay for DRAM in the device that only gets used seldom, in seldom occasions. Okay. Finally, I'd like to show some of the results that are attainable with the SEF architecture. This is a screenshot taken from a demo of an FPGA prototype of a SEF controller. This particular prototype had 32 die arranged on 8 channels. You can see at the front of the graph, the channels are labeled 0 through 7. Each die is represented by 2 colored bars, vertical bars, that represent I/O activity to that die. Blue bars are read activity to the die. Orange bars are write activities to the die. In this particular case, there were 3 virtual devices that were defined. The 3 virtual devices were actually running 3 different storage protocols. One was running ZNS, one was running standard block mode, and one was running a custom hyperscale FTL from one of our hyperscale partners. You can see in this graph that they exhibit total hardware isolation. At the back of the graph, the tall blue bars were a read-dominated workload that was dedicated to a set of 6 die. At the front of the graph, you can see 12 die that are running a workload that is roughly 50-50 read and write with the matched orange and blue bars across those die. And then finally, the 3rd virtual device was a write-dominated workload. We believe this is an industry first, the ability to simultaneously run different storage protocols on the same device. But that really isn't the most interesting aspect of this. We don't expect people to run this in multiple protocols at the same time in production. But what they will do is use the same device and deploy it on demand to meet different needs within their environment. And they can reconfigure the device in software to have it act as a ZNS device, a block device, or some other custom device. And furthermore, as new protocols and new storage applications develop in the future, SEF can adapt to them. So in summary, SEF consists of purpose-built hardware that's focused on managing the particularities of the flash media itself and giving full control to the host. SEF has a open source flash native API. SEF leverages industry standards and protocols wherever possible. SEF can be used to implement other protocols such as ZNS, or as demonstrated, a custom hyperscale FTL. And finally, SEF combines full host control with ease of use. For more information on software-enabled flash technologies, please contact Scott Stetzer at the email address at the bottom of this slide. We have a white paper available today. A microsite will be going live soon after the OCP Summit. And finally, this summer, the API will be published to the open source community. We're currently soliciting feedback from the hyperscale customers and finalizing the API. Thank you very much.
Okay, so this is a reminder that there is a Q&A panel where you can submit questions. We've had some questions come in, and I'm just going to be answering them more or less in the order they came in. So the first question was a question relating to both open channel SSD architecture and the light NVM subsystem, and whether or not how this relates to those two. So fundamentally, I would say that the open channel SSD was an attempt to solve many of the same problems of giving control to the host and being able to control things like latency and write amplification in the system. However, it partitioned the problem at a different point in the overall stack than we've done. And in particular, we believe that one of the biggest challenges to open channel was, in fact, the fact that you were responsible for all the low-level media details, which meant that, you know, as a producer of a system, you had to revisit your code and change it every time there was a new generation of flash. You had to change it for each individual vendor's flash that you wanted to support. And this, of course, is sort of a geometric expansion in your test matrix. So that's how I would place it relative to open channel, that it's a higher level of abstraction than open channel. And as far as the light NVM subsystem that's in Linux today, currently none of the hyperscale customers that we are engaged with are using that subsystem in their environments. So we haven't seen a customer demand for that. Certainly, it would be very easy to adopt this technology into the light NVM subsystem if there's a demand to do so. So no current plans, but we'll monitor demand for that. Okay. The next question has to do with when the documents and the API will be publicly available. That was actually answered at the tail end of the presentation. We expect the API to be published this summer in the August-September timeframe. One thing, the presentation was recorded in advance. The microsite is actually live now. And Scott, do you want to speak up and give them the actual URL for the microsite?
Yeah, happy to do so. The URL I've just posted up in the chat section of the presentation as well. But you can access the microsite at softwareenabledflash.com. All one word, no spaces, softwareenabledflash.com.
And that's also where you should be able to monitor for when the actual API is published and the exact location of the repository.
So this is Eric Reese. Let me take one other answer to the question about how things relate to open channel relative to what Rory just said. Of course, I endorse and agree with everything he said, but I would reiterate one point that really what we've done is look at the particular need of the market, which Open Channel attempted to address, and for us to take a look at it from a media-centric point of view. And it's our belief that the media management was the area that was the most trouble to the adopters, and in our engagements with them, that's what we came to understand. And so what people will see when they begin to really seriously explore software-enabled flash is that all of the flexibility that was imagined through the open channel approach is still available without all of the heavy lifting related to media management, both within a vendor and from vendor to vendor. Also, that same ease of use and abstraction relies from generation to generation. It applies to generation as they progress.
So, Rory, we had one question pop up in the chat from Satya Nishtala. He asks, are there specific application areas where hyperscalers are targeting initially for use of SEF?
Yes. So in particular, at the application layer, basically anything that's a candidate for essentially a log-on-log problem would be a very good candidate for going native to SEF. So if you know that you have data that is logically grouped together, has similar lifetime characteristics or lifespan characteristics, you can address the issues of write amplification very effectively through the ability to place the data with the SEF command set. The other thing is if you have applications that are extremely sensitive to latencies that can occur with a traditional storage subsystem, being able to exploit the full parallelism of the underlying media, as well as having control over the prioritization of commands, the scheduling of commands, and when and what is subject to garbage collection. That level of host control can really benefit an application that is latency sensitive.
So a big thank you to everybody that has come in and joined us here. There's still a pretty good crowd out there. We're happy to take any other questions if you would like to type them in. Okay, it doesn't look like there's any other questions out there. So for those that are still listening in, thank you very much for joining us. Please go to our microsite, softwareenabledflash.com, and keep your eyes out for the public release of the API this summer.